All right, so for titration, all right, we know the volume of standard solution, and standard solution is a solution that we know the concentration of. So, so that means we can also tell the concentration of standard solution. Okay, now with these two pieces of data, what do we actually know? If we know the well, we know the molarity, that's the concentration. And we have the volume, the moles. Okay, so we know the moles of the standard solution, whatever that we're using to titrate, to titrate with. And then we also know one more thing, and that is the volume of the unknown concentration solution, okay, which is the volume right here. So this is like, okay, now I'm not gonna say this is, I'm gonna say this is like the little dilution process, okay? The M1V1 is equal to M2V2. It's like that because we're basically looking at the moles. However, it is not exactly like a dilution because the mole ratio is not necessarily 1-to-1. And that's where we will use a word to describe the proportion. We can say at a titration, okay, we will stop at the end point. Okay, and we'll talk about what end point is in a moment. But at the end point, okay, the quantity of these two solutions or these two chemicals are supposed to be stoichiometric, simply meaning that they will follow the mole ratio. If it is 2-to-5, then the mole will be 2-to-5 ratio. Okay, so that's stoichiometric. All right. Now, as I mentioned earlier, a little while ago, I talked about the word endpoint, and so let me go ahead and throw those words here first. We have endpoint, and we also have the word equivalence point. Well, which one? It's a little bit tricky. So when we talk about acid-base titration, we use the indicator phenolphthalein, right? And that's what you did in Chem 1, and we say yes, that's the one that turns pink, and yeah, that's where it turns pink. So so we would say yeah, we would stop the titration when it turns pink. So that's called the endpoint. What is the relationship to the equivalence point?
Is equivalence point when you achieve the mole ratio?
So yes, the equivalence point is where you achieve the mole ratio in a very theoretical level. Okay, like, oh yeah, the moles are supposed to be stoichiometric, but endpoint is more of a actual thing.
Like endpoint is exactly when it should turn pink, right?
The equivalence point would be exactly where it turns pink, but endpoint is based on observation. So endpoint is going to approximate. Endpoint approximates equivalence point, and that's why when we do our titration, we will say, oh yeah, when you do your titration, at the very end, like when you start seeing pink, you gotta go slow. You do it drop by drop. You swirl it and let the base react. When you drip the sodium hydroxide into the unknown base or unknown concentration acid, let it dissolve, let it react, and then you try to achieve the lightest pink possible. Because we will need to record the volume used for the standard solution. If we let too much of the standard solution to go into the flask, that means we will overestimate the number of moles needed, and therefore we will overestimate the concentration of the solution. Okay, so this is also one type of lab question required, like lab question that you might anticipate for this unit. Okay, so far so good. Now, if so far so good, let me just say one more thing about this titration process before we move on to the actual calculation part, and that is a little procedure thing. Now, so if we do acid-base titration, of course, I'm going to fill up this pipette of the burette with the base. Okay, we are going to fill up the flask with the unknown concentration acid, and of course, we also put in the indicator of phenolphthalein. Now, how should we? Now we need to wash everything before we start. There's something we need to do to take care of the burette. Okay, so how to take care of the burette? Oh, good. Is that on the notes? Yes. So we would always wash it with the standard solution that you're using. Okay. Wash it with standard. Okay. And that's one more thing you need to be careful.
After the solution's already inside the unit.
Mm-hmm.
That's if it drops.
No extra air. Okay. Make sure you let it run. Make sure you turn the knob, let it run for a little bit so that there's no bubble at the tip. Because a lot of times people just pour it and then they just start. Make sure that you let it run. Make sure there's no bubble at the tip or anywhere in the burette so that when you record your volume, it is accurate. Okay. And that's another potential error. That they may ask you in the lab question and say, what if there is a bubble at the tip, and then the student starts the titration process, how would it affect? Okay, so again, you would think you add more, but you actually put less into the solution. So yeah, so far so good. So no bubbles, no bubble in the burette. Cool. All right, now. So now for us, whatever we're doing right now, we are only doing strong acid and strong base titration. Okay. Next semester, we will do strong acid weak base or weak acid strong base titration. And the math that we deal with is going to be a little bit more advanced. Okay, not hard, but it's just a little bit more advanced. But for now, we are just doing strong acid and strong base that kind of titration. So it's very important that you know all your strong acids and strong bases. With hydroxide. And also some of group 2. Yeah. Ammonia is going to be a little bit interesting. Oh, yeah.
Strong bases. Oh, and then the bottom group 2 elements.
Yeah, so bottom group 2, excluding magnesium. So anything from calcium and below, that would work. Okay, those are the strong bases. And for strong acids, HCl, HBr, HI, all the halogens. Okay, HNO3, H2SO4, And then the HClO4, HClO3, solubility. Magnesium, this is a very good question. Why magnesium is not part of it? So if you remember the calculations of lattice energy, magnesium is kind of small, right? So it illustrates, it has a very strong attraction to the hydroxide ion. So, and when we talk about, and I think that's a very good question to lead to the definition of strong acid and strong bases. It's all like the strength. It's equivalent to the number of ions, the amount of ions. Yes.
Some acids are strong.
So percent ionization for the acid or percent dissociation for the bases. Okay, it's got to be more than 95%. Okay, but for all these, we just assume that it's going to be totally ionized or dissociated. And one small thing that people may ask is that what is the difference between ionization and dissociation? They are like, well, if you look at the chemical equation, it's kind of hard to tell. Yeah. And it is also very important to start talking about the art of writing equations. Now, I'm going to start this little warning. Okay, not that it's very scary, but I do need to give you this warning. The success of the second semester will be built upon your ability to write equations. So when we say, oh, can you write an equation for ionization of acid? And we say, oh, sure. It's going to be acid plus water, giving you H3O plus and Cl minus. And since it's a strong acid, it is going to be a single-headed arrow. Next semester, when we talk about weak acid and weak bases, it will not be a single-headed arrow. It will be a double-headed arrow. Okay? So this is ionization because HCl was a covalent compound. And because of the interaction with water, they become ions. Whereas sodium hydroxide, for example, it is an ionic compound. And in water, it just breaks down to Na plus and OH minus. So this is what we call dissociation. I wouldn't say they are interchangeable, okay? Because fundamentally, they mean something quite different. So far, so good? Okay. Now, I'm not going to spend too much time on this because it's going to be pretty straightforward. So I'm going to say, all right, we have a titration of unknown concentration of H2SO4. Okay. Let's just say I prepared 20 milliliters of H2SO4 in the early mine. Oh, sure. Yeah, this one is good. I want to do this one because I want to do this one because the mole ratio is not 1:1. So NaOH, okay, and then we're going to write the equation later on. So okay, all right. So it takes this much of the sodium hydroxide to neutralize 25 milliliters of unknown concentration of H2SO4. What are the products of the acid-base reaction? Acid-base reaction would always, well, in this kind of acid-base, well, actually any kind of acid-base reaction, would give you water and salt. And let me go ahead and write down the state as well. And since it's not balanced, we should balance it. Okay. So the standard solution is going to be our sodium hydroxide. And again, it's all about our sensitivity. When you see volume, whenever you see volume, and then whenever you see molarity, you know you've got moles. Now, I'm going to do something slightly different here compared to whatever we did back then in Chem 1. We are not going to change the milliliters. Okay? And the reason why we are not going to change the milliliters is because we got milliliters for the other volume as well. So it doesn't matter. Okay? So if we have to deal with moles, then it becomes what we call the millimole. Okay? So we have that. Okay, so if you talk about the units, the liters got canceled out, but the milli stays. So that's how we have millimoles. If we actually put into the calculator, we say, oh, hey, at this point, we have access to the amount of moles or millimoles of sodium hydroxide. And then we say, well, okay, and at titration, they are in a stoichiometric relationship. 2 moles of NaOH.
1 liter on the bottom of that is, oh, you're saying.
So I broke down the big M to the actual unit, moles per liter.
Oh.
Yeah. So that's what I did. Oh, sorry. So the molarity, the mole ratio is 2 moles of NaOH to 1 mole of H2SO4. Okay. So technically, I've got myself the number of moles of H2SO4. So I'm going to go ahead and find out the moles right here. So that's basically 18 times 0.75 and then divided by 2. So I've got myself 6.75 millimoles of H2SO4. So to calculate the concentration of H2SO4, we simply do 6.75 millimoles of H2SO4 over 25 milliliters of H2SO4. So the milli would get canceled out. And the answer is 0.27 molar of the unknown constant. Well, that is the concentration of the sulfuric acid. And in real life, okay, if you have a job that's lab related, you do a lot of titration. Okay, so this is the kind of titration that we do for acid-base reaction. So again, you are putting the standard solution into the acid in the flask. So we stop titrating when the indicator turns pink. If we use phenolphthalein. And what I said earlier about the potential lab problem is that if you use more than you need, if the solution in the flask becomes like violet, okay, not light pink, but like actual purple, so that means you have used a little bit too much of the volume, so you will have more moles than expected, and then everything is just going to be inflated as a result. Okay.